We get a lot of data now out of the Texas Brine collects. We get it every day. We're analyzing it. Oil is green. Oil and brine total are in red, and brine is in blue. You can see the production rate over time since about the middle of October. It's following what looks like a straight line, but it's actually, if you drew a straight line on there, you'll see the last 3 or 4 points. This is the volume of gas flared out of the cavern. Again, the same type of curve. You saw a lot at the early on when they started flaring, and now it's more or less flattened out. One thing we've done is analyze the gas recovery data, and this supports what Bruce said about it appears things are slowing down with time. The gas recovery data, after they flare, they shut off the vent, or shut the valve basically, and let the pressure recover. And we can analyze these recovery curves to figure out things like permeability and stuff. But the simplest way to look at these is how the curve flattens out over time, because if you have a lot of gas coming in, you're going to get a very steep recovery curve because it can displace a little bit of brine and accumulate, so you get a very steep one. As the gas inflow rate declines over time, the curves get flatter and flatter. That is exactly what we're seeing. This is the 18th of October. This is the 9th of November. You can see how it's flattening out. So it most certainly does appear that hydrocarbons and gas coming into the cavern are decreasing with time. The pressure Bruce talked about is here. This is the pressure in the brine. We're also measuring pressure outside of the tubing, but this is the information you folks need. It was fairly stable for a long time at about 270. It dropped off to about 180, and it's been holding there. The exact cause of this drop off, we don't know. We've got some working ideas, one of which is the filling of the cavern is slowed down, so it's not putting as much pressure on the brine. I think that's a very valid observation. It may also be related to depletion of the gas outside the cavern, but right now we don't know, all right? These are just the real observations. You can see what's going on. These are the kind of things I have to evaluate every day to see if something's changing. The cavern infilling rate is shown here. You can see it started off here when they first tagged it. It's filled up quite a bit, but you can see at the top it is starting to flatten out, just like Bruce said. In fact, the last week it was down about a half a foot a day. The long-term average was about 2 feet a day, but now we're down less than half. These are, by the way, vertical depths as opposed to measured depth. Vertical depth means straight down versus measured depth being in the pipe that goes to it. The roof of the cavern is at about 3,400 feet vertical depth, so we have about 600 feet of cavern left to fill in. This actually, if you work in this business, this is actually kind of a decay curve, which means the rate of infilling is slowing, and we should expect that eventually it'll flatten out and won't be filling up anymore. I'm showing you all this because we need to understand the stability of the cavern. That's one place we've got some really hard data. We've got a lot on this project where we don't have data or we're just getting the data. As I mentioned, the inflow is declining over time. The cavern brine pressure is stabilizing, even though it dropped a bit. That actually may be a good thing. I interpret these to mean the cavern is reaching some kind of stability. So whatever was going on with the collapse zone and everything in the cavern, the data are indicating, and you've seen it, that the cavern is reaching some kind of stability, which doesn't mean it's totally stable, but it's trending towards a stable condition. The stability of the collapse zone outside the cavern, however, is still an unknown that we're working on. So the big piece, and this is where the seismic's going to help, and we're bringing in rock mechanics experts to help. The cavern appears to be stabilizing. We've still got to deal with the collapse zone here where the gas is coming up, causing the sinkhole and causing the problem here. So we're still dealing with the big part of the problem. We did add Itasca to the team. You don't know Itasca. I didn't even know until I started on this. But actually, they're a world-recognized expert in rock mechanics modelings and collapse subsidence. This is what they do. Most of it's for mining, but they evaluate this, they do predictions, they do modeling. We brought them down here last week. They were in Bayou Corn and Pier Park on Thursday. We took them out to eat at the Exxon station. Has good po' boys, by the way, good shrimp po' boys. Took them up in the helicopter, took them out for a boat run. John Boudreau took them out, showed them the bubbles in the swamp. We spent the better part of a half a day down here with them, answering their questions. We went around, we drove up and down the streets the street, I guess, in Bayou Corn, so they could see the houses. We had them all over the place because I wanted them to understand what we're dealing with and the people's lives that we're dealing with. And they very much appreciate that. When I say world-recognized experts are also from around the world. One's from England, one's from Norway, and one's from Serbia. They live in Minneapolis now, but they are an international group. The reason is the best people in rock mechanics tend to be trained in Europe. And they come here and they form the Itasca group. So these are world-recognized experts. Their job is to evaluate the stability